NASA's James Webb Space Telescope have a new and surprising discovery that sheds light on the shapes of distant galaxies in the early universe. In this video, we will explore this new discovery and what it means for our understanding of the history and diversity of galaxy formation. We will also learn how Webb was able to observe these newly discovered galaxies and what challenges and mysteries remain to be solved. If you are interested in this topic and the origin of galaxies, then this video is for you. Stay tuned and don't forget to subscribe and hit the bell icon for more videos like How do we measure the shapes of distant galaxies? To understand the shapes of distant galaxies, we first need to understand how we can observe them. As you may know, light travels at a finite speed, which means that when we look at distant objects in the sky, we are actually seeing them as they were in the past. The farther away an object is, the longer it takes for its light to reach us and the older it appears. This is what we call the redshift effect. By measuring it, we can estimate its distance and age and therefore observe it at different moments in the universe's history. To measure redshift for any object, we use spectroscopy, which is a very precise and accurate way of measuring redshift. But it also has some limitations. It requires a lot of time and light to obtain a high-quality spectrum, especially for very faint and distant galaxies. It also requires a prior knowledge of the expected positions of the spectral lines, which may not be available for some types of galaxies. So there is a way of measuring redshift, which is to use photometry, which is the measurement of the brightness of an object in different colors or filters. The shape of a galaxy spectrum is not only affected by its redshift, but also by its properties such as its star formation rate, its dust content, and its metallicity. These properties determine how much light a galaxy emits at different wavelengths, and how much of that light is absorbed or scattered by the interstellar medium. By comparing the observed shape of a galaxy spectrum with theoretical models or simulations, we can infer some of these properties and also constrain its redshift. This is how Webb was able to measure the shapes of distant galaxies in the early universe using its powerful cameras and filters. But what did it find and how did it prove us? Let's find out in the next section. The shapes of the newly discovered distant galaxies in the early universe are not what we expected. According to a new study led by Viraj Pia, a NASA Hubble Fellow at Columbia University, many of these galaxies are flat and elongated like surfboards and pool noodles rather than round like volleyballs or frisbees. This study used Webb's data from the Cosmic Evolution Early Release Science (SEER) survey, which is one of the first surveys to observe the early universe with Webb. They targeted a patch of sky in the constellation of Orion and observed it with 11 different filters covering a wide range of wavelengths from the near-infrared to the mid-infrared. This survey detected more than 1,000 galaxies with redshifts ranging from 0.5 to 10, corresponding to distances of 5 to 13.4 billion light-years and ages of 1 to 13.4 billion years. Among these galaxies, the study focused on 300 of them with redshifts between 6 and 10, corresponding to distances of 12.4 to 13.4 billion light-years and ages of 400 million to 1 billion years. These are some of the earliest and most distant galaxies ever observed, and they are very faint and hard to see even with Webb. To measure the shapes of these galaxies, the study used a technique called GalFit, which is a software that fits mathematical models to the images of galaxies and estimates their parameters such as their size, brightness, and orientation. They used two models, one that assumes that galaxies are round or spherical and one that assumes that galaxies are flat or disc-like. By comparing the goodness of fit of these models, the study was able to determine which one was more likely to represent the true shape of the galaxy. The results were surprising. They found that about 70% of the galaxies were better fit by the flat model and only 30% by the round model. This means that most of the early galaxies were flat and elongated rather than round and symmetrical. The study also found that the flatness of the galaxies increased with redshift, meaning that the farther and older the galaxies were, the flatter they were. These findings are in contrast with what we see in the nearby universe, where most galaxies have spiral or elliptical structures and are round or oval in shape. How can we explain this difference and what does it tell us about the evolution of galaxies? Let's explore these questions in the next section. The shapes of distant galaxies in the early universe are different from the shapes of nearby galaxies because they are influenced by different physical processes such as gravity, gas feedback, and mergers. Gravity is the main force that shapes galaxies by pulling matter together and making it rotate. It tends to make galaxies round by smoothing out any irregularities and clumps. However, it also competes with other forces such as pressure and angular momentum, which tend to make galaxies flat by spreading out the matter and making it spin faster. On the other hand, gas is the raw material for star formation, and it plays a crucial role in the evolution of galaxies. It can cool down and condense into dense clouds, where stars are born. It can also heat up and expand due to the radiation and winds from massive stars or the jets and outflows from supermassive black holes. These processes are called feedback, and they regulate the star formation rate and the gas content of galaxies. Finally, mergers are the collisions and coalescence of galaxies, which can trigger bursts of star formation and change the morphology and dynamics of galaxies. They can also affect the shapes of galaxies by making them more round or more flat, depending on the mass ratio, the orbital parameters, and the gas fraction of emerging galaxies. These processes are responsible for the diversity and complexity of galaxy shapes that we observe in the nearby universe. However, in the early universe, these processes were different, and they resulted in different galaxy shapes. In the early universe, gravity was weaker because the matter density was lower and the dark energy was less dominant. This means that galaxies were less bound and more susceptible to external perturbations such as tidal forces from neighboring galaxies or cosmic shear from large-scale structures. In the early universe, gas was more abundant because the universe was younger and less processed by stars. This means that galaxies had more fuel for star formation, and they formed stars at a much higher rate than today. However, gas was also more turbulent due to the effects of feedback, which prevented the gas from settling into a thin and stable disk. Finally, mergers were more frequent because the universe was smaller and denser, and galaxies were closer and more chaotic. Galaxies were less massive and more irregular. This means that galaxies had more opportunities to interact and merge with each other, and they were less likely to preserve their original shapes. These factors combined to produce the flat and elongated shapes of the early galaxies, which are different from the round and symmetrical shapes of the nearby galaxies. These shapes also reflect the different stages of galaxy evolution, from the initial collapse and fragmentation of gas to the formation and growth of disks and bulges to the final assembly and transformation of galaxies. By studying the shapes of distant galaxies in the early universe, we can learn more about the physical processes that shape them and how they changed over time. We can also compare them with the shapes of nearby galaxies and see how they are related or different. This can help us to understand the origin and evolution of galaxy shapes and how they are connected to other properties of galaxies such as their mass, luminosity, color, and morphology. However, there are still many open questions and challenges that remain to be solved. For example, how reliable are the measurements of the shapes of distant galaxies given the limitation of the data and the models? How do the shapes of distant galaxies depend on other factors such as their environment, their stellar population, and their dark matter halo? How do the shapes of distant galaxies affect their observability and detectability, and how can we correct for any biases or uncertainties? And how do the shapes of distant galaxies compare with the predictions of theoretical models or numerical simulations, and what can we learn from the agreement or disagreement? These are some of the questions that astronomers are working on using Webb and other telescopes and instruments to advance our knowledge of the early universe and the origin of galaxies. And we can expect more exciting and surprising discoveries to come in the near future. We hope you enjoyed this video and learned something new and interesting. If you did, please give it a like, share it with your friends, and leave a comment below. We would love to hear your thoughts and questions on this topic. And if you want to see more videos like this, please subscribe to our channel and hit the bell icon so you don't miss any of our future updates. Thank you for watching, and see you next time.